Hello and welcome to the Pre-College Program STEM at Home Activity Day, where we're talking about what moves water around the globe, what forces move water around the globe. I'm Sean Rowe. I work for Oregon Sea Grant at Oregon State University. I do marine education and science communication, as well as research on how people learn. And what I'm going to show you today are some of the activities we do in my class called Communicating Ocean Sciences. Have you ever wondered what forces move water around the globe? You probably know something about this already. I'll give you a minute just to think about that before we move in and show you some activities that you can do at home right now or later. You can watch me, you can pause me to set them up and then do them. Observe it for yourself, create your own experiments about these forces that move water. Usually when I ask people this question, the first answer they give is wind. That's pretty obvious. Wind pushes water. But can wind actually move water around the globe? Is it strong enough to move the water in a serious way? Or does it just kind of blow carefully across the top? This is something you can model, how the wind moves water in the ocean, very simply. I'm going to move the computer so you can see this little setup here. I've got stuff that you can get at home pretty easily. You probably can't see me now, so let's turn this up a little bit. Pretty easily. A little tank. This is just a small shoebox size plastic tank with water in it, some things that float, some things that might sink, and a straw. And what I'm going to do is demonstrate for you whether we can move the water in this very small ocean basin just with wind. So you can see, here's what I'm going to do. I'm going to take a straw and I'm just going to blow the water. Just like wind would, blowing across the surface of the ocean. You can see it rippling, but can you see it moving? Let's find out if it's really moving. I've got a ping pong ball here. I'm going to put it right there. And I gave my kids this task earlier, which is, can you make that ping pong ball move to that side of the ocean from Japan to Oregon? Let's try. All right, that was pretty easy, but did you see what I did? I blew the ball with the wind. So I created wind by blowing across the surface of the ocean, but I aimed it right at the ball. And because it sticks up above the ocean, it actually moved. Let's try something else in my little bucket here that might sink. Hey, here we go. How about a binder clip? It sank. Can I move it by blowing it? No matter how hard I blow, that thing's not moving. That's because it doesn't stick up above the water, so it can't catch the wind and sail like a sailboat or like the ball did. But how about this? Can I make this ball move from this side of the ocean to that side of the ocean without blowing the ball, only by blowing the water? So this is an experiment you can try yourself. Why don't you give it a try? Pause me and give it a try. I'll give you just a second. Did that work? I'm going to try it myself now. Let's see what I can do. First, I'm going to blow this way. But I'm aiming just at the water. Watch. The ball's not moving very well. I'm blowing pretty hard. What if I blow that way? It's really hard to get the ball to move. What if I put the ball right in the middle? Can I now make it move without blowing it? How about that? I was able to make enough ripples at the surface of the water to actually push the ball straight across. So what do you think? Can wind create movement of water in the ocean? Absolutely. Movement of water in the ocean we call currents. But there's other kinds of movement too, like tides and things like that. Today we're going to talk about currents. Looks like we can create a small type of current right at the surface with the wind only. I'm still having trouble moving that binder clip though. I'm going to try one more time to blow really hard, like hurricane force winds on this water. That binder clip's not going anywhere. What do you think? When you think about currents and what you know about currents in the ocean, do they only exist at the surface of the ocean? I'm going to move my slides forward now. We've demonstrated that we can blow the wind across the surface of the water and it can move things across the ocean that way. We've also seen that it really doesn't get much of an effect down below. No matter how hard I try, I can't move that heavy binder clip from the bottom, which sank. And this water is not very deep, especially not as deep as the ocean is. So what causes currents below the water? Let's talk briefly about what currents are. Currents are patterns of movement of water that are pretty permanent, right? Some of them are temporary, some of them happen for a short period of time, but for the most part, currents happen and stay happening. They're very predictable. We know where the main currents are and which direction they flow. Sometimes currents can change direction. That's also pretty predictable. So what's driving that if it's not wind? I got two other demonstrations that are going to help you experiment with this and figure it out and see how it works yourself. This is a large fish tank filled with room temperature water, and we're going to look at one kind of force that moves water here in currents. And then over there, I've got another one on with two bottles that I'm going to demonstrate as well. Let's talk about the fish tank. Whoops, let's go back. I'm going to demonstrate to you, and you can try this at home as well, that you can create a current in a relatively large ocean. You could do this with a smaller fish tank, 1.5 gallon size, 2 gallons, 10 gallons. I'm going to show you that we can actually start a current in this fish tank with only water. Now, how's that going to be possible? Well, I got several things here. One is a cup, 2 cups, 2 binder clips, 2 straight pins, thumbtacks, and food coloring. I also have some ice down here and some hot water, which I'll bring over from the kettle in just a second. And here's what I'm going to do. You can set this up too while I'm doing it. Take your cup, paper, styrofoam, even plastic, take your thumbtack and push it into the bottom right there. Okay? Then I want you to take the cup, clip it somehow or tape it somehow to the side of the tank. I'm using these binder clips just because it's convenient for me, but you could use tape as well. Now I'm going to do the same thing with the other side. I'm going to take the cup, I'm going to poke the thumbtack in the bottom, I'm going to bring it to this side of the tank, and I'm going to clip it on. There you go. Now, what am I going to do next? Into this, I'm going to put, on one side, a bunch of ice, regular ice cubes of any kind. I'm going to pretty much fill the cup up with that. And then to that, I'm going to add a little bit of plain water, room temperature water. I'm going to fill it up to the top of the cup with the ice in there and let that sit for a second. In the other one, I'm going to put water that I've just boiled in this kettle. So I'm going to take this and carefully pour hot water into this cup. Now, to make it easier to see what's happening, we've got food coloring, everybody's favorite stuff for science, right? So I've got blue food coloring, which I'm going to use to represent cold water, and red food coloring, which I'm going to use to represent hot water. What I'm going to do is put this water, this food coloring, right into the water in the cups. So I'm going to drop about, I don't know, 1, 2, as many drops as I can get out of this tiny, almost empty bottle of blue food coloring into that cup. And then I'm going to put drops of red food coloring into this cup where I put the hot water. It's helpful to stir it around a little bit after you get it in there, just to make sure it's dispersed all the way through. Now, actually put a little red in there because we're almost out of blue. What do you think is going to happen when I take out the thumbtacks? Let's start with the hot water. I'm going to reach carefully under and pull out the thumbtack, and you'll see immediately that the water starts to flow out of the cup through the tiny hole. Watch that water. What is it doing? Observe how it's moving through the water. You can see that it starts to sink immediately, but then what happens? At the same time, I'm going to pull this one out with my bluish purple water on this side to represent cold water. And we're going to watch to see what happens over there. Can you see that color coming out? You can see that it also starts to sink pretty quickly. Oh, it's dark enough for you to see. Maybe I should add a little more food coloring to that. But you can see it. Can you see this coming through? Is that showing up on the video okay? You can see the second color. Great. So you can see this sort of slightly purplish blue red over here coming down, and this bright red over here coming down. Notice what they're doing. Observe what they're doing. Watch what you see happening. Look at what's happening to the red water, the hot water. It's coming in, it's sinking, but then it's starting to rise back up to the surface. And in fact, you can see that it's starting to move across the surface of this water. This water is hotter than the water in the tank, and it's definitely interacting with that water differently than this one is. You can see that this one is spiraling down. How well can you see that on the video? You may need to get a little bit closer. And it's sinking pretty much straight to the bottom. Watch it sink. I may pick up the computer and move it over here because I'd really like for you to see from the side what this looks like. Try not to get seasick when I move the computer. Look here. You can see that the red has pretty much come back all the way to the surface, all the way through the water. It's only sitting at the surface. Whereas on the other side, this kind of purple is sinking pretty quickly to the bottom, just straight down. It's not mixing much with the other water. Can you see it spiraling down there? Great. What do you think will happen if I let this sit for some time? Let's talk about what's actually happening. First, we got the blue cold water, in our case, a little bit purple, more purple than blue. We got the red hot water. What's happening with the cold water? As you can see, it's sinking. It's sinking all the way to the bottom. In fact, the bottom of the tank is starting to turn a little bit purple. Let's move it down here like this so you can see it. And the top water in the tank is starting to turn all red. That's because the cold water is sinking inside the tank of room temperature water, and the hot water is rising. What makes that possible? That's what we call density. Now, I'm sure you all know something about density and have heard about density, maybe even spent a lot of time thinking about density. It's one of the most interesting things in all of science, and especially ocean science, because it makes a lot of things happen and a lot of things possible. One of the things that it makes possible is this: water can move in different ways inside other water. So we're creating a condition here where warm water is moving in one direction as it hits regular temperature water, and cold water is moving a different direction as it hits regular temperature water. I'm going to briefly talk about this. What is density? Density has to do with the amount of a substance that's packed into a space. It's mass divided by the volume of the space. Cold water is more dense because the molecules that make up water are closely packed together in a space. And because they're closely packed together, they take up less space. The cold makes them shrink almost together, whereas the warmth, the heat, actually makes them expand, makes the molecules and the distance between the molecules grow bigger in the same amount of space. That water is less dense. So it rises up, whereas the colder water, which is more dense, sinks down. Is this enough to create a current? Now, you can see that the water is definitely moving, but is it creating a current in this ocean? What we're going to do is we'll move on to our next activity. We'll come back to this and see what it looks like in about 5 minutes and see what you think, if we've actually been able to create a current. Back up there. So what we've just demonstrated is that temperature can, in fact, produce movement of water. Differences in temperature, to be more exact. Warm water hitting regular temperature water or even cold water behaves one way differently. Cold water behaves a different way. And they set up these patterns of movement when you put them in a closed system. What else can do that? Let's try another demo to do this. And this is another one that you can very easily do at home with salt. So we know that the ocean is full of salt. Salt water makes up the ocean. It's not the same as the water in your sink. It's not the same as the water we drink. It's full of salt. It has what we call salinity. And I'm going to demonstrate with another activity over here that salinity can also create current. And that's because, just as we saw with the hot and cold water, saltier water sinks and fresh water rises. How can we show ourselves that at home? Well, here we've got two regular size, shape, water bottles, Coke bottles, any kind of pop bottle will do the same thing. Plastic bottles with a small lid. Take the lids off, fill one with regular water out of the tap. In fact, I'm going to add a little bit more to make it really full. You can do the same thing at home. Fill up one of these bottles like this. Over here, in this pitcher, I've got some salt water that I prepared earlier simply by mixing salt with water. And I made it pretty salty, really gross. You don't want to drink it. You don't want to pour it on your plants after you're done because the salt might kill your plants. It's not good for them anyway. And I've turned it green, and that's just so you can see what happens. And I'm going to fill up the second bottle almost to the top. Now, what I'm going to do takes a little bit of practice. You can learn how to do this very easily, and I recommend you try it. I also recommend you try it over something like this tray that I've got here so that if you spill any water, it doesn't go anywhere. What I'm going to do is I'm going to take this bottle with the salty water in it that I've colored green. I'm going to turn it upside down on top of this bottle, and we're going to see what happens. What do you think will happen? Will they mix? Will they stay the same? Will the salt water stay in this bottle and the fresh water stay in that bottle? Let's see what happens. All right, I'm going to try to do this very quickly. It's actually easier if you have a piece of paper or a playing card that you can put underneath this, on top of this one, underneath this one as you make the switch, but you can do it this way as well. All right, ready? 1, 2, 3. All right, spilled a little bit, but I want you to observe what's happening. Look at that. What do you observe? What do you see? What I observe when I step back and look at it, whoops, is that the salty water is sinking directly down into the other bottle of water. Let's take a piece of paper and put it behind there real quick so that you can definitely see what's going on as you look through. Look at that. I can see movement in the top. In fact, what I can see at the top is that water's going up. I can completely understand the water going down, but I can also see this water going up. I can literally see the water changing places in these bottles. And one way you can tell is that the color in the bottom bottle is already starting to change. It's starting to look more green already, sort of greenish blue. What we've got here is, in essence, a current movement of water from one depth to another depth, up and down now, based on the fact that one is salty and one is fresh. I really want to just let this sit here, and I'm afraid it's going to spill. So I'm going to move it off of the tray, which is not very steady. There you go. Take a look at that. If you try this at home, you might try it twice. Try putting the fresh water on top first and see if it behaves the same. See if the same thing happens when you put the fresh water on the top instead of the salt water on the top. Let's look back at our temperature now real quickly. What happens when this is done? We have a question online. What happens when this is done? What's it going to look like at the end? I think that's an excellent question. Why don't we let it sit for a second and we'll look back at the temperature water. We'll come back to this and let's see what it looks like. All right, we've just demonstrated two kinds of density. Density created by a change in temperature and density created by a change in salinity. Why is saltier water more dense than fresh water? For the same, kind of a similar reason. There's simply more stuff in it. As soon as you put in salt or sugar or sand, anything that will dissolve in water, well, sand won't dissolve, anything that you can dissolve in water is going to actually make that water heavier because it makes it more dense. It makes more stuff packed into the same amount of space, makes it more dense. That makes it sink faster than water that doesn't have anything else in it. So, and you can, I don't know if you guys can see this or not. You should really do this at home because one of the things you can see up close is that there's actually a very spiraling current going straight up into this salty water and another spiraling current going straight down into the fresh water. We have another question. What if you put something that does not dissolve in water like oil? That's an excellent question. Does anybody have an idea about what might cause that or what might happen in that case? What happens when you put oil in water? Maybe that's an activity for another day. Yeah, I have one answer online. Oil floats. That's exactly right. So, you know, one of the problems that you have in an oil spill, so if oil spills off of a tanker or if you have an oil spill off of a recreational boat in a harbor, the oil doesn't sink to the bottom. The oil floats on the surface. That's why seabirds and sea lions and seals and otters and animals like that that live at the surface of the water primarily or go in and out of the water a lot are subject to a lot of danger from oil spills, whereas fish, crabs, things that live at the bottom don't suffer in the same ways. The oil floats right at the top. What would happen in this case where you try to put if you try to put the oil at the bottom and the water at the top? Do you think the oil would stay at the bottom and the water would stay at the top, or do you think it would flip over? My guess, having never done this exactly, my guess is that it will flip. And in fact, somebody online is saying that yes, it will flip. Yeah, oil will in fact change this position. It'll do exactly what we're seeing here. The oil in this case will almost appear to rise up into the water, through the water to the top, and the water will do the opposite, sink down through the oil to down here. So the sinking we can understand is kind of intuitive. The floating up of something like oil is a little bit weird, and it's really interesting to see. In fact, if you go online and look for how to make a homemade lava lamp, that's exactly how they do it, with oil, colored, and water. Let's look back at our temperature activity here for a second. Another question, or actually a comment. That is why during an oil spill, oil gets to the beach. That's exactly right. What's pushing that oil to the beach when you have an oil spill? Any ideas? Most likely it's wind pushing across the surface, because remember we were easily able to blow an object across the surface of our little tiny ocean with a straw by creating wind. Oil floating on the surface, and this is another activity you could try very easily with the activity setup we just did with the ping pong ball floating in the water. Boil some kitchen oil in there, put a little bit of canola oil or olive oil on top of the water, and then try to blow it with your straw and see if you can move it or if it sinks. All right, now I want to look back at our temperature activity, and then I'm going to talk a little bit more about some of the science details. Can you guys see what's happened here? It's actually really fascinating. They've started to mix a little bit, but if you look closely, you can actually see the water moving. And I'm going to try to put this a little bit closer so you can see it. And again, you can recreate this at home with any size tank of water, as long as the sides are clear, at least one side's clear, so you can see what's going on. I've just put white paper, in this case paper towels, on the back with some tape to make sure that you can see the difference more easily. But the water's still coming out. If you look over here at the hot water, it's still streaming out, and it comes down about halfway through the tank because of the gravity that's pulling it out of the cup, but then it rises back up and literally is moving across the surface of our small ocean. On the other side, I can still see the water coming down. In fact, right here, you can see a very clear line of purplish blue going straight to the bottom. And notice it does not rise back up the way the red water does. It just continues to sink all the way to the bottom. And in fact, it's starting to spread all the way across the bottom of the tank. So look at our cool looking tank now. Our cool looking ocean has 3 different layers. It's got a purple layer of water at the bottom. It's a little hard to see. It's got a more clear layer in the middle, which has a little bit of red and a little bit of the purplish blue, but it's got a very clear red layer at the top that's not sinking. These things are moving. One's moving to one side of the tank, the other's moving to the other side of the tank. If we let this sit long enough, we'll actually create a circular current through the top and bottom of this tank, but also from one side to the other. And we could literally move objects in this water using simply the difference in temperature created and the currents that creates. What happens if you're using other colors is one of the questions we have. You'll see the same thing. When you're trying this at home, I recommend you do it with darker colors than lighter colors because they're easier to see in the water, obviously. And you might make it, the fun part about using food coloring is you can make it as dark as you want. Make a really dark purple and a light green. Make a really dark red. Make a really dark blue. Any color will work for this. I'm using red, why? To represent and help you remember that this is hot water, and blue to help you remember that this is cold water with the ice in it. Remember, you got to put that ice in there to make it really cold and make that water really hot to really see the difference. Even if it's just a little bit different, you'll create a current, but it won't be as obvious very quickly. So the next question that I have here on the slide is, can ice drive currents? In fact, ice does drive currents, and that's one of the reasons that currents exist. At each end of the globe are poles covered with ice. That ice both puts cold water into the ocean and takes heat out of the ocean. Takes heat out to make ice, puts cold back in. And as that happens, it starts to create a current around the land masses that are covered in ice. So you actually get heat coming into the ocean from the sun at the equator, at the tropics, heating up the water, which starts to move north or south toward the poles. That water hits the cold, cold ice shelves and icebergs. And what happens to it? It becomes cold and it immediately starts to sink. It sinks fast and it sinks with a lot of force. Sinks all the way down, all the way to the bottom of the ocean where the water is already cold. What happens when the cold water hits the colder water? Some of that water starts to rise back up again, which pushes water up toward the poles where it gets warmed by the sun and creates this movement again. So the poles, the temperature difference between the poles and the equator, where it's warm, help create movement from north to south or south to north of the currents. We call this movement thermohaline circulation. So water that is thermo is hot, heat. Haline is salt, in this case, saline. Thermohaline is circulation caused by differences in density, which are caused by differences in heat or cold temperature, and salinity, amount of salinity versus amount of freshness of the water. I'm going to show you, I'm going to exit this screen because I want to show you a really fantastic video of exactly what this looks like, created by scientists at NOAA. So this is a video, you can find this simply by Googling thermohaline circulation. So watch what happens. This is a picture of the globe. It's an animation that's going to show you the currents, the Great Ocean Conveyor Belt, which is a current in the entire ocean created almost entirely by differences in temperature and salinity. So you can see as we move toward the North Pole in Greenland, Iceland, water's coming up from the south. It's hitting the cold water, the cold ice shelf, and it's sinking immediately. As it sinks, it goes to the bottom of the ocean, which is shown here based on these maps and models of what the bottom of the ocean is. We've mapped some of that, but we actually have not mapped most of it, as you may know. And you can see that that water starts to move in the direction of where the water came from. It's replacing the water that has moved, the hot water that has moved north and is traveling south as the water in the south is rising up. This continues to happen. In fact, that water pushes through the equator all the way to the South Pole and does it again. This conveyor belt moves water through the entire globe. So the water in the Atlantic Ocean is not simply Atlantic Ocean water. It is really ocean water that is global. It's moving. Water is moving all the time. These huge currents create all kinds of things that are important for humans. This is one of the ways we travel on the ocean. We facilitate travel. It's one of the ways that large animals migrate in the ocean. It's a really, really important driver of ocean life. Oops, excuse me. Let's get rid of Chris Packham back there. So there's one ocean technically is the question I have online. Absolutely. We think about this as one great ocean. They teach you the 7 seas. They teach you about the Atlantic Ocean, the Pacific Ocean, the Indian Ocean, the China Sea. These are actually one large ocean that covers the entire Earth. All are connected, all are interconnected. And one of the main ways they're connected is by this movement of currents that are constantly shifting large volumes of water from north to south, from the equator north, from the equator south, where it's warm to where it's cold, from where it's cold to where it's warm. And it doesn't just go north-south because the Earth is spinning. That water starts to move east-west, west-east. Take a look at it and think about what's pushing this water. I want you to look at one more thing on our demonstration over here. If you can see this, I'm looking at the side of my tank now, and I'm looking at my hot water, which is still continuing to come out. Look at this beautiful arc it's made. The hot water is streaming down, gets this far, and streams right back up. It's creating exactly this kind of current we were talking about. And then that water is moving across the top of my tank. I can actually see where the new water has come out of the cup. It's darker red than the water that started to mix up. And it's literally moving toward the cold water in the other side, toward the cup of ice. And vice versa. At the bottom, it's harder to see, but the cold water, I can still see streaming down. You may be able to see it through my tank on the video, streaming down here, and then flowing across the bottom toward us over here. Absolutely fascinating and beautiful. That's a super easy activity for you to do at home and experiment with different kinds of ways of creating currents. You can combine these. So there was this great question about the oil. You can absolutely put oil in this tank and see what happens with that as the water starts to move in this circulation pattern. You can try recreating the wind on the top of this tank while the heat is moving things around. You could put salt water in one of these cups and fresh water in the other cup and see what you can create. Once you've set this thing up, you can do a lot of different experiments basically to learn about what drives the ocean currents. What's this got to do with ocean careers? Does that seem like a funny jump? I know a lot of you are interested in how you become a person who does science in the ocean. One of the major ways we study these kinds of things right here is through work done at Oregon State University. How do we see these currents operating? Well, we don't have a system like this where we can actually we can model it all we want, but how do we know this is really happening in the ocean? Oceanographers, climatologists, people who go out on ships for research, people who work with mammals like whales and dolphins, people who work with fisheries and how large fish like tuna move around in the ocean, or even endangered species like turtles and how they move and where they go, and predicting that and understanding that. They work with animals and currents constantly. Anybody who works with the beach understands currents. If you live in Oregon and you want to know when's the best time to go fishing, you are basically using your understanding of currents to do that. And the people who study that work at Hatfield Marine Science Center, work at Oregon State University in oceanography, in biology, in geology, in marine mammal research, and management, understanding how to best protect fisheries and promote fisheries. Anybody who works in the ocean works with currents. Everybody who works with the ocean works with density. The best way to get involved with that is to start to think and be interested in and follow up on things like this. What makes this water move? Your curiosity can really drive that learning and your ultimate career goal. Now, I'm not an oceanographer. I'm not a biologist. I'm a communicator and an educator. I work in the ocean because it's fascinating to me. I work with topics like this because they're fascinating to me, but I do not have a science degree. I have a psychology degree. So you don't have to be a scientist to be interested in and work with the ocean. And at Oregon State University, you could come and work at any of those things. It's one of the most fascinating things about working at a big university. People all over the university in all kinds of jobs are working on lots of similar contexts like the ocean, looking at it from different ways, bringing different perspectives to that. The one thing they have in common is they all have a curiosity, they all have interest, and they've all gone to college at some point to do something related to that. Share your page on chat. Sorry. I just got a message online that said it was telling me to do something. I'm going to share with you my webpage because that's one of the places that you can learn more about what I do and the kind of work done at Oregon State University. Am I still sharing screen? Yes. I'm going to go to the chat and I'm actually going to grab my website. Do we have any other questions while I'm doing that? I have another question online while I'm pulling that up, which is what do you love most about your job? The thing I love most about my job is that I get to work in all kinds of cool places with all kinds of cool people. So I do most of my work at the coast in Newport. And one of the best things about working in Newport is that you get to work with fishers, you get to work with scientists, you get to work with managers, you get to work with all kinds of people who are interested in the ocean and the uses of the ocean, whether it's fishing or surfing or understanding the science of the ocean. Everything that you can imagine wanting to do with the ocean, people do at the place where I work. And what's so great about that is that I get to learn all the time about things I never knew about from that every week. All right, here we go. Here's my website. I'm going to put it in the chat. If you want to know more about what I do and how I work in the ocean and with ocean scientists and with students who want to know about the ocean, with families who want to visit the museums at the coast and learn about the ocean, you can look at my website, freechoicelearninglab.com. If you just Google Free Choice Learning Lab at Oregon State University, you'll get there as well. All right. Well, I want to thank you all for joining us today. I hope you try these at home. On the original advertisement for the activities and for the webinar, there's a list of materials that for each one of these activities: wind, salinity, and temperature, so you can recreate it. We'll also be doing some more in the future on some other really interesting topics with activities like this that you can do at home or in your classrooms. All right. Thank you very much.